Hello, and welcome to the section 4.4. We're going to talk more about solubility. We've already discussed solubility in terms of ionic compounds and which kinds of ionic compounds are soluble in water. We're going to look a little more in depth at some compounds that are not necessarily ionic and what that means for their solubility. First, let's look at solutions and define solutions. We've been talking a lot about them, but let's just go back to the basics and make sure we all know what a solution is. A solution is a homogeneous mixture. Its components are uniformly intermingled. It's homogeneous. So, in other words, a sample from one part of the mixture is the very same as a sample from any other part of that mixture. Here we have a person drinking some coffee. Their first sip of coffee is the same as the last. That would be homogeneous. It would be a solution. Let's look at the parts of the solution. Solution contains a solvent and a solute. The solvent is present in the largest amounts. The solute would be in the smaller amount. So here we have sugar being poured into some water. The water is the solvent. The solute is the sugar. It's in the smaller amount. You can also remember the solvent always dissolves the solute. When we have aqueous solutions, water is the solvent in those by definition. Here are some examples of solutions. You may or may not have thought of these as being solutions before, but according to our definition, they are. Not all solutions are aqueous. Air, for example. Let's say we're talking about a solution of air, and we want to look specifically at the nitrogen in the air. Well, the solvent is a gas. Its state is a gas. It's the air. The original state of the solute is the nitrogen in the air. It's also a gas. And this whole solution is a gas. Antifreeze in water would be an example of the solute. The antifreeze solute is a liquid. The solvent is also a liquid, and this whole solution is a liquid. Brass. Brass is an example of a solid solution of copper and zinc. We have both our solute and solvent as solids, and the solution itself is a solid. Carbonated water is an example where the solvent is a liquid, water. The solute is a gas, the CO2, and the final solution is a liquid. Here's another example of seawater, where we have a mixture of some different states. So solutions are not always aqueous. They can be other things, and they aren't always just liquids and solids, like as in our sugar solution. They can be a mixture of some different states. Let's look at, once again, our ionic substance, sodium chloride. Here's our crystalline sodium chloride salt. When we dissolve that into water, what is really happening in that solution? Well, remember, it's breaking into the individual cations and anions. These are dispersed throughout the water. And what happens in the water is that the chloride and sodium ions themselves are surrounded by our water molecules in such a way that the water molecules will orient themselves in this manner. We have water where the hydrogen ion, or the hydrogen atom within the water molecule, is slightly positive. The oxygen atom is slightly negative. So the water molecules will arrange themselves around the chloride ions in this way, where the hydrogens are facing the chloride ion, and the oxygens will be facing the sodium ion because that oxygen is slightly negative in charge and the sodium ion is a positive charge. So this is actually what is happening on a molecular level when something dissolves. The different molecules and the different ions are arranging themselves in this way. So what kinds of molecules can water dissolve? We've been looking at ionic molecules. Water can dissolve ionic compounds. What about other kinds of compounds? Let's look at these terms polar and non-polar molecules. We've talked about this a little bit in the past, but let's just revisit it. Here are some examples of polar molecules. We have water. Water is very polar. Remember our Lewis structure for water here? It's bent. One side of the water molecule is charged in a slightly different way than the other side. The hydrogens are slightly positive. That oxygen is slightly negative because it has a higher electronegativity, so it's pulling on the electrons more than the hydrogens are, so it pulls electrons more towards itself, has a slightly negative charge, and because the water molecule itself is bent, this side of the molecule has a slightly positive charge, and these sides here have slightly, this has a slightly negative charge, excuse me, and these are slightly positive. In the same way, these molecules are polar. They have a place in the molecule that pulls electrons more towards itself and has a slightly negative charge. It has places in the molecule where there is a slightly positive charge, and it's different overall within the molecule. Here, anytime you have an OH group, an alcohol group like this, a hydroxyl group, you're going to see polarity, as opposed to a non-polar molecule. This non-polar molecule is a very long chain of carbons with hydrogens on it. It is the same all the way around. It doesn't pull in one way, in one direction or another. It doesn't pull the electrons anywhere in particular. It's uniform all the way around, so it's very non-polar. Molecules that are like this, petroleum, oil, they contain long hydrocarbon chains. This is called a hydrocarbon chain, if you'll remember from biology. Here's an example of what happens when you try to mix a polar water molecule with a non-polar fatty acid oil, long fatty acid chain. They separate. They do not mix. So, in other words, water, being polar, does not dissolve a non-polar molecule. And we have a really nice rule for this. Let's look at that. Like dissolves like. You've probably heard that before. Water is polar. Water dissolves polar molecules. Like dissolves like. A non-polar molecule will dissolve another non-polar molecule. That's why when you're working with, for example, oil paint, gasoline, or other types of petroleum products work really well to dissolve them and to clean them. You cannot wash your oil brushes in water. It doesn't work because like dissolves like. So here is a picture of some of the reasons for that. We have water, very simple molecule. When water is in a beaker, we have a lot of hydrogen bonds that are being created. A hydrogen bond, here's an example of that. We have our water molecule. We have our slightly positive hydrogen forming a hydrogen bond with this slightly negative oxygen from a different water molecule. In the same way, we have this slightly positive hydrogen forming a hydrogen bond with this other molecule of water and the oxygen, the slightly negative oxygen end of it. You can see the slightly negative oxygen from this water molecule forming a hydrogen bond with the slightly positive hydrogen from a different water molecule, and right here as well. And in a large beaker of water, you have many, many, many of these hydrogen bonds forming. And this is what is happening in a solution. We have other ions or other particles coming in, and unless they can adequately replace some of these hydrogen bonds, they will not be able to dissolve in that water solution. So we know that a charge, something that has a charge that is polar, right? Like our alcohol, it has an OH on the end. That is able to pull charge in one direction. It can come in and replace some of these areas in our water that have hydrogen bonds. Chlorine also, we have ions, right? The little chloride ion and the sodium ion. Those are other examples where they can come in and replace these hydrogen bonds in the solution, and that is why water is able to dissolve molecules like this. Here are some qualitative terms associated with solution concentrations. These are terms that you are, I'm sure, familiar with, but let's just review them, make sure everybody knows them. A saturated solution is one that contains as much solute as will dissolve at that temperature. So if I am adding sugar to some water and I'm stirring it and I'm dissolving it, and I'm continuing to do that until the point where if I add any more sugar molecules to that water solution, they will not dissolve. They will fall out of solution. The point just before I get to that is saturated. That solution is saturated. It cannot hold even one more molecule of sugar without and dissolve it. Unsaturated solution is a solution that has not reached that limit yet. Okay, so it has not reached the point at which it cannot dissolve anymore solute. Supersaturated solution is an example, would be if I take my sugar solution and I heat it, I'll be able to add more sugar to it. Then when I bring that to its limit at that elevated temperature and I cool it down, as long as that sugar stays dissolved and it doesn't fall out of solution, it is supersaturated then when I cool it down. We know the terms concentrated and dilute. Concentrated is just a relative term, a relatively large amount of solute. Dilute means we have a relatively small amount of solute. Here's sort of a picture of that. Here we have a dilute amount of pinkish colored solute in the solution, and it is becoming more concentrated, obviously, as I go this direction on that scale. Here are some factors that affect the rate of dissolution. I can dissolve things quicker if I have more surface area, right? I can also dissolve things quicker if I stir or elevate the temperature. Here are just some examples of that. And think about the surface area. If I have sugar cubes and I place a sugar cube in a solution of, or in water to get a sugar solution, and I take a different beaker and I put sugar crystals, powdered, it's all powdered crushed sugar, right? The granulated sugar that you get out of the bag of sugar. And I put that in in water. Which one do you think will dissolve faster? Well, the crystals of sugar have much, 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 much more surface area than these cubes. These cubes just have those 6 different sides of surface area, and those crystals have a lot of surface area. So increasing surface area will help us dissolve things faster. Stirring helps us dissolve things faster. It allows us to move particles about, move the different molecules about, exposing more surface area, and we will be able to dissolve things more quickly, dissolve solute more quickly. Temperature, obviously, here's just an example. If we raise the temperature, our solute will also dissolve more quickly. Ideas for advanced proficiency. Actually, prove that to yourself. Create your own experiment to determine if these factors actually do increase the rate of dissolution. Create your experiment, time it, show me that indeed that really does, that really is true. Or design an experiment to test principles of like dissolves like. Show me your experiment. How does soap work? How is it able to mix water and oil in order to clean? That's an interesting idea right there. The EPA is responsible to ensure safe drinking water. Find out how pure drinking water is required to be. You might surprise yourself. So here, those are some advanced ideas. I'd really love to see some of you do some of these. So maybe you could pick a few of those to do, and I look forward to seeing you in class.